Today, you are going to discover the answers to the top 10 most frequently asked questions about FRP and Australian pedestrian design codes. Good morning and welcome to our webinar on demystifying the Australian pedestrian design codes. I'm Kelly Stewart, Marketing Manager at Wagners CFT, and I'm here with Wagners CFT Design Manager Jason Zischke and Technical Lead Ali Mohammed. As the design manager at Wagners CFT, Jason coordinates all design work required for our construction projects, including technical drawings and plans. Jason has been with Wagners for more than 13 years, bringing a wealth of knowledge regarding drafting and technical software used to design construction projects. Meanwhile, our pre-construction manager, Stuart Baker, was to be presenting today, but unfortunately is sick. So we welcome Wagners technical lead, Ali Mohammed, to step in Stuart's place. Ali oversees all technical elements of Wagners CFT projects globally. He is a structural engineer specialising in civil composites with a strong technical background in FRP products at the material level, individual components and full-scale structures. Ali is passionate about FRP and believes it is the material of the present and future. Plus, we're also joined today by Department of Transport and Main Roads Acting Director for Structures, Evan Lowe. Evan is a registered chartered engineer, civil and structured, with extensive asset management, design and project management experience across a variety of industries, including light and heavy rail, airports, utilities, roads and tunnels. Welcome, Jason, Ali and Evan. Before we get started, just a few webinar protocols. We are recording today's event and will make the recording public via the Wagners CFT YouTube channel. Unlike our usual webinars, you can ask a question anytime during the presentation and we will answer them during the segment you've asked the question in. Questions can be asked via the chat tab, which you will see at the top of your screen, indicated by a speech bubble. Today we will be discussing Australian Standard 5100, AS 2156 and AS 1170, the walking track classes, Austroad's Guide for Cycling and TMR's design criteria for bridges and other structures. So let's get started. Over to you, Jason and Ali.
All right. Thank you, Kelly. Jumping straight to the first question. Is the Australian bridge design code AS 5100 necessary in all locations for pedestrian boardwalks and bridges? Doesn't need to be FRB for all types of pedestrian and boardwalks. So basically, to simply put, the AS 5100 is not required for all the pedestrian bridges and boardwalks, and that mainly depends on the location of the structure, whether it's like near a roadway or it's subjected to vehicle access. So basically, the location and the utilization of the structure, that's going to determine the applicability of AS 5100. And when we say the applicability of AS 5100, we're talking about the single components of AS 5100. So, for example, if we're talking about any type of pedestrian bridges subjected to water forces, so AS 5100 is still going to govern, because basically it's the only available code in Australia that addresses the flood loads. So basically, we need to refer to part 16 of AS 5100 to address the flood loads on pedestrian bridges that not been fully designed to AS 5100. And when I say fully designed to AS 5100, it mainly means like the vehicle loads and also the deflection limit. So basically, the deflection limit as per AS 5100, it's usually like it's L over 600. That's of the overall span of the bridge. However, that's more suited for basically for concrete or traditional material bridges, where any small deflection or when any additional deflection that might cause some damage or like micro cracks in the material. However, with FRB, because of its high strength to stiffness ratio, the deflection limit or the serviceability limit is what governs the design. So basically, by omitting AS 5100 for the bridges on boardwalks that away from the roadways and that's not subjected to vehicle loads, that will result in way more cost-efficient design. And now for the visual learners that we have in the room, basically like the next slide show.
Billy, can you show the next slide? I think I've got the wrong one sitting up. I'll just cancel my share, but the screen doesn't seem to be showing through the right one.
Absolutely, no worries. Just let me pull up that presentation.
Doesn't seem to be showing the right.
Okay, so I think this is the one you wanted, Ali.
Yep, this is a slide. Yeah, so basically, this is a visual representation of two bridges. Both of them are the same length, slight difference in the width, and that's gonna mainly gonna affect the UDL overall UDL loading on the bridge. But if one of them is being designed for AS 5100, that one the Edgewall Pedestrian Bridge, that one is being designed for AS 5100. That's for TMR. The second one on the right hand side is a Scottville Pedestrian Bridge, which is also the same length, but it's been designed for AS 1170 and AS 2156, which means basically slightly lower design loads. Like there's no point load, which is on the point load is significantly less than the one on Edgewall Pedestrian Bridge, and that's going to mainly affect the decking and the joist system of the bridge. But the overall design of the truss bridge is still going to be governed by the UDL and the 5 kVA loading. However, these two bridges, basically, as you can see, one of them is heavy-duty bolted truss bridge to suit or to be compliant with AS 5100. The other one is riveted light-duty truss bridge. Both of them basically like serve the pedestrian use, and both of them basically they meet like the vibration requirement and the pedestrian comfort level. But as you can see, there will be like a substantial difference when it comes to the design and the cost efficiency of these two bridges. And the next question, I'll hand it over to you, Jason.
Yep. All right. The second question we'd like to help clarify was what track do I require for my pedestrian structure? Now, I agree that terminology within 2156.1 is very vague. Although I found one website that provides excellent clarification on this. That's the New South Wales National Parks site, which I think they just minute. That just zoomed in and out. I was hoping that moved to the next page. You can, yeah. So which is shown here, and most other states within Australia have something similar. And from here you can, it's easy to read that if the track is short and flat, we can class it as a track class 1. But as the grades and the length in the overall track changes, that's when it changes from track class 1 through to 2 and so on. So as it gets a bit more, needs a bit more fitness, so to speak, as well. So moving on to the next slide, if you can, Kelly. So from that point on 2156.1, outlines basically just the minimum requirements. So, although you've got minimum requirements, we can always go a bit higher than that when we're required, but still leave the classification at a lower level. But as you can see here in the image, on the left-hand side, we've got an area of 2.5 metres by 2.5 metres, with 23 people standing in the one point, and that's what indicates as what is 3 kPa. And on the right-hand side, we've got a bit more crowded, but that's a representation of 5 kPa with 36 people standing in that same square. Both are very crowded, so I don't think that if we go 3 kPa that's not enough. You can see both are very, very crowded, and then you times that area out by the whole area of the structure, and that's what we're designing to. Pass back over to Ali.
Thank you, Jason. Good visual representation of the 3 kPa and the 5 kPa. Basically, that applies to every single square meter of the structure, whether it's 500 meter long boardwalk or whether it's like 20 meter transfer bridge.
Yeah, exactly.
Yeah. The next question is about it's about DDA compliancy, and the question says, do all DDA compliant structures need to be walking track class 1? So basically, the simple answer is no. And basically, one statement can summarize the answer for all this question is that basically all track class 1 structures need to be DDA compliant. However, not all DDA compliant structures need to be track class 1. So basically, like a track class 2 structure can also be a DDA compliant if we provide like the single components in terms of slope and grab rail and what have you. So basically, that can also make it a DDA compliant track class 2 structure, let's say. The DDA compliance is mainly a client requirement, and also it mainly depends on the location of the structure. Basically, whether the structure, like is in a crowded area where we expected basically a disability access is required. However, if the structure is in the middle of nowhere and there are a set of stairs at both ends of the structure, so DDA compliance is basically can be omitted from the design requirement. The next slide show a good photo basically of a walking track class 3 structure, where it's been designed to be to be like a DDA compliant by providing the grab rail. However, the other components of walking track class 1, like the balustrade infields and is not being incorporated in this structure, so it doesn't qualify to be as class 1 structure, even though like it is a DDA compliant. And I will hand over to Jason for the next question.
Yep. So moving over to the next question.
Jason, I might just jump in there for a second as well and just remind everybody, if they do have some questions about each individual top 10 question that we're covering, please feel free to jump into that chat and just throw the question in there, and the guys will be more than happy to expand upon whatever they're talking about and answer your question as well. Sorry, Jason, for interrupting.
Yeah, that's no problem. Yes. On to 2156.2. Is it still a relevant standard to be used despite being withdrawn? The simple answer is yes. Standards Australia clarifies this on their website, saying that this standard can still be used despite being withdrawn, where no other standard covers that a part or the whole part of a design of a structure. So one of these parts that we use a lot still for 2156.2 is just the determination of different handrail types to be used on a structure depending on its track classification. Now I'll pass back to Ali.
Thank you, Jason. The next question says, which code governs under compliance for FRB pedestrian boardwalks and bridges? So basically, there are a few different codes that dictates the requirements for FRB, or basically for all handrail systems. So basically, there's like the AS 2156, also like the AS 5100, the AS 1170, and even like for the access structure AS 1657. And also there's the Osroad guide for cycling part 6A. So basically all of these codes are governed equally, and basically the specified codes need to be met for the structures that is being designed. So basically all the minimum requirements, mainly dimensional requirements, let's say, mainly dimensional requirements need to be met for all the mainly the dimensional requirements of that specified code need to be met on that specific structure. There's a slight difference when it comes, or maybe like this. Yes, there is a difference when it comes to the loads and the deflection requirement between AS 1170 and AS 5100, and again that also need to be accounted for when it comes to the design, and that's also need to be basically specified in the design process. The next slide show a few different handrail types and options that have been designed over the years. So basically we put together the following showcase. So basically the top left is a walking track class 3 compliant. However, it doesn't meet the Osroad 6A requirement due to the fall height. It's maybe it's a little bit hard to see in this photo, but also it doesn't meet the DDA compliant due to the lack of grab rails on the ramp section. This is due to the ramp being too steep to conform, and therefore this requirement became redundant. The top right photo meets track class 3 and DDA compliance. However, it doesn't actually require a grab rail due to the shallow slope or shallow grades of the ramp section. The central photo would be fine under the condition of AS 2156 up to class 2 for fall heights, and it does include DDA compliance. However, there is an elevated section that wouldn't meet a track class 1 requirement without a balustrade. Bottom left photo, we have a DDA structure on grade, hence the grab rail and we wouldn't actually need a balustrade under any 2156 Oxford or NCC requirements due to the low level nature of this structure. And finally, we have a bottom right, the photo at the bottom right side of the slide. Basically, this structure is about basically 4-meter elevation at its tallest point. So it does require a grab rail and balustrade inflow. It doesn't, however, need to meet the Oxford requirements for a grab rail design, as it's primarily used for a lookout and want basically subjected to cyclists. Yeah. So basically, this will cover this slide, and I'll hand over to Jason for the next question.
Right. Okay, so our sixth question we get normally asked is what level of geotech is generally acceptable in the foundation design of pedestrian structures? The design of most pedestrian structures is completely different to your average house slab design that only requires a soil typing geotech report. As you can see on this drawing, the next one if you can, Kelly. Here we have a pedestrian bridge that we designed in Auckland, New Zealand. These structures that we generally design are founded generally upon deep foundations, as you can see. So we need a more in-depth view of the ground's conditions in as many spots as possible. And as you can see from this bridge, it's only 66 meters long, and we have variations in the soil from the left-hand side to the right-hand side of this bridge in the subsoil layers. And for us to accurately design these foundations, we rely totally on the geotechnical engineer's determination on bearing capacities, skin friction, and lateral soil stiffness properties that these layers have been detailed as. Right.
Yeah, the next question is about the wave and flood modeling for pedestrian structures. So basically, this question is straightforward, and it's kind of like the answer itself. So basically, like for every structure is within a flood zone, basically it will be required basically to design that specific structure for water forces. And basically will require a hydrology report, which usually come like from historical data and with some theoretical prediction for the next events in the next 100 years or 500 years, depends on the design requirement. And basically we will require, like the velocity, the water velocity, and also the water level, and also like the cross section of the creek, just to determine how deep the creek is with respect to the structure. Same thing basically like with the wave loads. So the wave loads will be subjected to all the structures that is within the coastal zone, and also subjected basically like to wave loads. In other words, basically where the wave loads can be high enough to reach the structure or the substructure or the whole structure. So for that specific cases, like basically we talk with the coastal engineers to provide us basically with the wave analysis reports and provide us with the loads in kVA to design the structures for such extreme forces, which in many cases it's what usually govern the strength limit design of the structure. The next slide basically shows a good photo of bicentennial boardwalks in Early Beach. It is subjected to wave loads, and basically we have engaged a coastal engineering firm to provide us with the wave loads, which is in kVA, and we applied that kVA basically, or that loads to the structure and design the structure basically to be adequate to withstand such extreme effects. And I'll hand over to Jason for the next question.
So moving on, another question that arises when considering AS5100 is the effects in the difference of the deflection when designing glass composite fibre structures. On the slide here, we have two different designs. The left is a 10-metre bridge design in full consideration to AS5100 deflection requirements. As you can see here, the thickness of the floor structure is about 500 mil, whereas on the right-hand side, we have a structure that's just been designed to AS1170 deflection requirements with much smaller floor thickness of 400 mil. Both these bridges were designed to take the same live loads, but it's just purely the deflection limit that governs here as to that thickness. You might think why this is, and the reason is that the tighter deflection on AS5100 structures, and that is, I think, purely based to the importance of the structures that are usually governed by AS5100, being major highways and rail bridges. However, not all pedestrian bridges need to kind of cover this same importance. If we move over to the next slide, I've got a bit of a simple idea of what this all means, because I know sometimes span over, when we throw numbers like span over 600 and span over 250, you might think that that's quite a big difference. However, a 10-metre girder bridge under AS5100 deflections would only equate to a maximum deflection of 17 mil at mid-span, whereas under AS1170 deflections, that's the span over 250. That maximum would only increase to 40 mil. So that's only a difference of 23 millimetres, or for the oldies out there, that's about an inch. So not exactly much over a 10-metre span. I'll throw it back to Ali.
Yep. This is the final question for me before I hand over to Ivan. As you say, like, save the best for the last. This is my favorite question. It's about the 200 kilonewton lateral restraint minimum lateral restraint load that's coming from the AS5100, and whether it's applicable to basically to pedestrian bridges or boardwalks, not necessarily FRP. So before I answer this question, basically clause C9 in the commentary section of AS5100.2 is very self-explanatory when it comes to this requirement, and basically like it explains why this requirement is being specified in the code. Like mainly it's basically to enforce the good practice of using positive connection when it comes to the bridge girders or boardwalks girders or joists. Use basically a positive connections and not rely on the gravity or friction to eliminate the lateral displacement that could come from accidental impact, or that could come basically like from minor earthquake. So this is mainly applicable basically like for the super tees and massive concrete girders where their gravity load is substantial, so it can resistant like some wind load and either like maybe like minor earthquake, mainly by gravity and friction. However, that is not applicable to the small pedestrian bridges, mainly because the positive connection is used all the time, mainly because they are not heavy enough to resist wind load and water forces. So basically, when we design the whole structure, the lateral load is mainly coming from the wind load and the water forces. Talking about FRP structures, the earthquake load isn't most of the time doesn't govern the lateral design loads of the structure, mainly because of the lightweight of the FRP structure, and the earthquake load is usually like a percentage of the overall mass of the structure, which could be like 10-20%, depends on the seismic region. The final point that I would like to highlight here in response to this question, like this 20 kilonewton lateral restraint load is to allow for accidental impact that could come from traffic that's going underneath the bridge, whether it's like a vehicle traffic or whether it's a vessel traffic that's if the bridge is going over a water body. So for each project, the location of the bridge is basically what specify the requirement, or whether this specific lateral load is required for this specific application or for the specific structure or not. Because at the end of the day, if the structure is in the middle of a national park going over a small creek, you wouldn't expect basically a 200 kilonewton accidental impact load that's coming from a vehicle or a vessel. And also at the same time, we need always to remember is basically all of these structures are positively connected or fixed to the headstocks or bridge abutments or whatever foundation type being utilized in that structure. And that is the main point of AS 5100, is to enforce the positive connections for such structures. Now I will hand over to Evan from TMR to address the final question.
All right, thanks for that. Look, so we get commonly asked in the department around how these codes are being used and implemented, and certainly from Queensland main road transport projects, that's covered by the department. It's rarely just boardwalks and walking pedestrian bridges. Therefore, TMR's document provisions can, from time to time, appear overly robust when applied to a boardwalk or a bushwalking sort of a bridge. For the department, the principal design reference for all bridges in Queensland is the Australian standard, AS 5100, which has recently received extensive updates. To augment the bridge design code, which includes the design criteria for bridges and other structures, the department also has the options for designers of pedestrian and cyclist bridges to achieve value for money. So those are key documents that you could refer to on our website. And in these suite of technical guidance notes, we also make reference to the likes of AS 1170, AS 2156, and a vast range of other documents as well. You would find that the design criteria from the department is predominantly intended for designers of road bridges carrying active crowd loads, motorised traffic, or even potentially infrastructure that is within proximity, which the department deems as high risk and potentially is high consequence as defined by the department's risk appetite if a failure does occur. So look, it's important to note that the department welcomes alternative criteria if changes can be reasonably justified, and that if there's a substantial case for it, whether this is sustainability, whether or not you do a life cycle analysis, or you provide sound engineering, including risk assessments, it would all be considered. But these alternative criteria should always be sought early in the design process as a matters of resolution as defined by the design criteria, which would, for the department, involve submitting a case at the early stages. And on to the next question that we get asked is, what are the issues we commonly face? So for the department, look, pedestrian bridges are definitely fascinating structures. Pedestrian, by definition, has the ability to enhance personal mobility. It improves community health, and also promotes actually social equity. And if this definition includes cyclists, lime users, and people with disabilities, in the department we call them active transport bridges. Compared to vehicle bridges, let's say motorised traffic, The load supplied to active user bridges are relatively light. Now, this offers opportunities for a lot of design innovations, and it can also enhance urban landscape aesthetics. You can make pedestrian bridges as simple as possible, or you can make it as elegant and sophisticated, providing your client's willing to pay for it. So generally, clients and designers alike are trying to find that delicate balance between aesthetics and functionality. As a designer, look, I think you must determine the most appropriate type of structure for the available options that you have, whether it's a girder, truss, arch, slab, cable. And you also need to select the right combinations of materials. That includes concrete, steel, aluminium, timber, FRP. And prime considerations from my perspective are safety, resilience, durability, and cost effectiveness. Look, these decisions will be influenced by the spans to be overcome, the social context of the bridge, and the constraints offered by the environment below the bridge itself. Whether it's a waterway, whether it's a road, the demographics around that bridge. Do you put throw screens, not throw screens, just handrails? And this often will involve a huge consideration of a number of possible configurations and a comprehensive options analysis. And some of the design elements that designers really should consider is aesthetics. Consider design life, how long you really want this bridge to last for without doing any major maintenance. Collision risks, could it be impacted? The user envelope, the access requirements, maintenance, and as everyone's mentioned here around deflections, you also need to consider dynamic behavior. So if you're walking across the bridge, how do you want the users to feel? And certainly little structural components like drainage and bearings. And that's all. Thanks.
Right. Thank you very much for your presentations. Just let me do some bit of stop sharing and that here. And swap some presentations around. Okay, so that's the end of the presentation from Jason, Stuart, and Ali and Evan. I see there's not too many questions there in the chat at the moment. So I'm just going to give people a chance, if they do have a question that you want to ask this panel while we've got them here and they're available, pop it in the chat. And I'm just going to quickly share my screen and tell you a bit about some new product collaborations that Wagners are doing and what webinars we've got coming up next, while you have a bit of a think and put some things in the chat there. All right, so Wagners CFT is proud to be working with our newest product collaboration with RKM Roller Company. RKM heavy duty but lightweight composite roller provides lightweight and less noise in comparison to the normal plain steel rollers for mining conveyors. The key features include it's 50% lighter than steel with advanced wear properties. Its superior stiffness and flexural strength comparable to steel, low noise and high performance sealing to prevent rock jamming and ingress of contaminants. If you want to find more about the RKM composite conveyor belt roller, use the QR code there that's on the screen at the moment, or I'll quickly just put this code in the chat for you so that you can go and have a look at more information on that one as well. Our next webinar is on the 30th of July. We're going to be looking at a recent trial in Port Macquarie of an electric vehicle charger inside a streetlight pole, and exploring how the community liked the technology. What was feedback from the community and where to next with this technology. Guest speakers for that webinar are going to be Brad Trethaway from Essential Energy and Wagners CFT product specialist utilities James Lorimer. So again, if you'd like to register for that webinar, you can use the QR code that's on the screen there now, or again, I've just popped that link into the chat facility so that you can to register to attend that one as well. I just wanted to tell you about the webinar that's coming up in August as well. We're going to discover how Magrin and Associates and Larcom General Builders designed and constructed a world-class ecotourism experience on South Australia's Kangaroo Island. We'll be joined by Magrin Technical Director and Senior Engineer Will Souter and Kangaroo Island-based builder Jake Nolan from Larcom General Builders. It's going to be a good one. So again, you can use the QR code that's on the screen, or I've just popped that URL into the chat file as well. And of course, as per usual, I will make sure that everybody gets an email with all of these upcoming events. So it does look like we have a bit of not a question, but my experience from Max Willison. Choice and application of all codes are made simple and clearer when the client provides clear direction on the service level of the network the structure is part of. I believe more questions should be asked during scoping of a job before selecting a codes. Also, compliance with AS does not absolve risk. This must be measured in SID. This is highlighted in the front of AS 5100. Ali and Jason, did you want to speak to that? Comment from Max Willison.
Yeah, I agree with Max. So basically, it's a question that we asked basically at the beginning of the project, and that's what just to make sure that the proposed structure is going to meet the intended use of it. Basically, it's basically like meeting the client or the asset owner requirements of that structure, and all of that comes basically by asking the right questions and reaching that agreement and basically like confirming a event point to reach that delicate balance between functionality and aesthetic.
All right. I see, Eric, you've got your hand up there as well. Eric, if you'd just like to pop your question into the chat facility, that would be great. All right. It doesn't look like we've got too many more questions coming in there. Ali and Jason, is there, or Evan, is there anything else that you'd like to say before we wrap up the webinar today?
Not from my perspective, but certainly, look, the department's certainly open and keen to have more conversations around this area. I think Max has made a very important point there that certainly there's a lot of things that needs to be discussed up front in a project for you to drive the right outcome. So certainly from a department's perspective, we look forward to that.
Excellent. Thanks so much, Evan, as well, for taking part in today's webinar. We appreciate that. I'm just going to quickly share my screen here. Oops. I'm just putting up the feedback form from today's webinar. If you could take 2 minutes of your time and complete the feedback, that would be fantastic. I'm just going to put the link into the chat there as well. These feedback forms help us craft the webinars that are coming up. So if you can take 2 minutes out of your day today and just complete that feedback form, that would be fantastic, and we'd appreciate that. We're going to wrap up today's webinar, and we're actually going to go out on the fantastic little video that we came in on that was showing an array of pedestrian infrastructure that has been constructed from Wagners fibre reinforced polymer. I'd like to thank everybody for coming today, and we look forward to seeing you for those 2 great webinars that are coming up in July and August. We'll see you next time.